Hi, this is Neelima from Team Victoria. I'm here to discuss on the topic geometric transformations, which plays an important role in computer graphics. So before getting into details, let us know how geometric transformations are applied in computer graphics. If we have to move an object or change the shape of an object, instead of redrawing it, we transform the coordinates of the original object in order to achieve the resultant transformed object. Hence, geometric transformations helps in repositioning the graphics on the screen and change the size or orientation. Now let's get into the details. These are our team contributions. Transformations are categorized based on the dimensional plane. Transformations done in a two-dimensional plane is referred to as 2D transformations. Transformations can be done in different ways. They are translation, scaling, rotation, and sharing. Translation is moving an object from one position to different position in a coordinate plane. As you can see in the picture, triangle has been repositioned in the coordinate plane, which is moved below the x-axis, and the shape of the triangle is not changed. Now let us take an example of translating a point in a 2D plane. Let us assume that there is a point x, y, 2, 1, and if we have translated it to a different point, that is 5, 2 with the translation vectors 3 and 1, they are represented as x dash equal to x plus tx and y dash equal to y plus ty, where x dash and y dash are the translated point and tx and ty are the translation vectors. Hence, the translation matrix is represented as below: x plus tx and y plus ty. 2D rotation. In rotation, the object is rotated a particular angle from its origin. Now let us assume a point x, y at an angle phi from the horizontal axis with distance r from the origin. After rotating at an angle theta, the new point is x dash y dash. Now let us derive the rotation matrix. By using trigonometric equations, the original coordinate x, y can be represented as x equal to r cos phi and y equal to r sin phi. Same way, the new point x dash y dash, that is the rotated point, is represented as r cos phi plus theta and y dash equal to r sin phi plus theta, where theta is the new angle of rotation. Now, according to trigonometric formula, r cos phi plus theta can be written as r cos phi cos theta minus r sin phi sin theta, and r sin phi plus theta can be written as r cos phi sin theta plus r sin phi cos theta. Now, substituting the equations 1 and 2 in 3 and 4, we get x dash equal to x cos theta minus y sin theta and y dash equal to x sin theta plus y cos theta. Now, we can represent this equation as a matrix representation as below: x dash y dash equal to cos theta minus sin theta cos theta into xy. Here the positive angle rotation matrix is cos theta minus sin theta cos theta. Rotation angle can be positive or negative. The negative angle rotation matrix is represented as cos theta sin theta minus sin theta cos theta. Another type of transformation is scaling. Scaling done in a 2D plane is known as 2D scaling. Scaling transformation is used to change the size of an object. Dimensions of the object are either expanded or compressed. So there are two types of scaling. One is uniform scaling and the other is non-uniform scaling. Uniform scaling is nothing but expanding or compressing an object with the same scaling factor uniformly in all directions of the object. For example, if you see in the picture, the quadrilateral is being expanded by twice uniformly in all the directions. Expansion or compression of an object done with different scale factors in different directions is known as non-uniform scaling. For example, if you see in the picture, the triangle has been expanded in one side and compressed in another side with different scaling factors 0.6 and 1.4. In order to derive the matrix representation of scaling transformation, let us assume the original coordinates as x comma y and the scaling factors as sx and sy. Now the scale coordinate x dash and y dash are represented as x dash equal to x into sx and y dash equal to y into sy. Now from this equation we can derive the matrix notation of scaling transformation as below, where x dash and y dash is equal to sx 0 0 sy into x and y. Here the scaling matrix is sx 0 0 sy. Homogeneous coordinates. In order to perform sequence of transformation, the steps we need to follow include translating the coordinates, rotating the translated coordinates, and then scaling the rotated coordinates to complete the composite transformation. To shorten this process, we need to convert 2 by 2 matrix to 3 by 3 matrix. We add an extra dummy coordinate for such conversions. Representing the point by 3 numbers instead of 2 numbers is called homogeneous coordinate system. Any Cartesian point x, y can be converted to homogeneous coordinates by p dash xh, yh, h. Let us consider homogeneous coordinate x, y, w. The line joining this point and the coordinate origin intersects the plane w equal to 1 at a point x by w, y by w, 1. This transformation treats a two-dimensional homogeneous point as a point in three-dimensional space and projects this three-dimensional point to the plane w equal to 1. Each 2D position is represented with homogeneous coordinates x, y, 1. Now based on the homogeneous coordinates, the transformation matrices are represented in this way. Translation matrix is represented as 1 0 0 0 1 0 tx ty 1, and the rotation matrix is represented as cos theta minus sin theta 0 sin theta cos theta 0 0 0 1, and the scaling matrix is represented as sx 0 0 0 sy 0 0 0 1. Inverse transformations. The process of moving a transformed object to its original position is known as inverse transformations. Inverse transformation matrices are represented as below. Inverse translation matrix is represented as 1 0 minus tx 0 1 minus ty 0 0 1. That is T inverse of tx comma ty equal to T of minus tx minus ty. In the same way, inverse rotation matrix is represented as cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. That is R inverse of theta equal to R of minus theta. Inverse scaling representation of matrix is 1 by sx 0 0 0 1 by sy 0 0 0 1. That is S inverse of Sx, Sy equal to S of 1 by Sx, 1 by Sy. Composite 2D transformations. A series of multiple transformations performed one after the other is known as composition of transformation. Now let us consider the transformation to rotate an object about its center point xc, yc. And this can be done in a series of basic transformations. Firstly, translate the object by minus xc, minus yc so that the center coincides with the origin. And now perform a rotation about the origin and then translate the object by xc, yc to return to its original position. Now let us see how the individual transformations are performed by matrix multiplication. Firstly, translation done by minus xc, minus yc is represented as below, where the original point is multiplied by the translation matrix to achieve the new translated object. Now rotate the translated object about its origin by multiplying resultant translation matrix with rotation matrix. Now this resultant matrix should be multiplied by the translation matrix in order to move the object to its original position. Now the resultant matrix of the series of transformation is cos alpha minus sin alpha, xc minus cos alpha into xc, plus sine alpha into yc, sine alpha cos alpha, yc minus sine alpha into xc minus cos alpha into yc, 0, 0, 1 into xy1. Now let us consider the composite transformations in scaling. A scaling transformation alters the size of an object. This operation can be carried out for polygons by multiplying the coordinate values x, y of each vertex by scaling factors sx and sy to produce the transformed coordinates x dash, y dash. In a fixed point scaling, there are three steps to scale an object about the fixed point. Firstly, translate the object so that the fixed point coincides with the coordinate origin, and then scale the object with respect to the coordinate origin, and then use the inverse translation of step 1 to return the object to its original position. And now the composite transformation matrix for this process is Sx0 xf into 1 minus Sx, 0 Sy, yf into 1 minus Sy, 0, 0, 1 into xy1. Order of transformations. Does order of transformation really matters? So let us see in which case it matters and in which case it doesn't matter. While performing multiple 2D rotations, order doesn't make any difference. R1 into R2 is same as R2 into R1. In a composite transformation, the order of individual transformations is important. For example, if you first rotate, then scale, then translate, you get a different result than if you first translate, then rotate, then scale. Composite transformations are built from left to right. If S, R and T are scale, rotation and translation matrices respectively, then the product SRT is the matrix of the composite transformation that first scales and then rotates and then translates. The matrix produced by the product SRT is different from the matrix produced by the product TRS. And you can see that in the picture. Computational efficiency. Homogeneous coordinates are a simple and efficient means to perform geometric transformations by matrix multiplication. The entire set of geometric transformations can be combined into a 4x4 matrix or into a 3x3 matrix in the case of 2D coordinates. Homogeneous coordinates exhibit several benefits. Like uniformity is maintained in all transformations, complex transformations can be built by combining individual simple transformations by matrix multiplication. Complex transformation can be performed by first calculating the overall transformation matrix by multiplying the individual matrices and then applying the resulting matrix to the data. Simple inversion of the transformations by inverting the transformation matrix. 4x4 matrices are supported by various standards and graphics hardware. Rigid motion is another type of transformation where the object can be moved in such a way that the relative distance between the points of the object stays the same and the relative position of the points of the object stays the same. There are four types of rigid motions. They are translation, rotation, reflection and glide reflection. Let us see how they are done. Translation. In a translation, everything is moved by the same amount and in the same direction. Every translation has a direction and a distance. Rotation. A rotation fixes one point and everything rotates by the same amount around that point. Every rotation has a rotocenter and an angle. When you notice the pictures of both translation and rotation, you can see a common point over there. That is, the position of the object has been changed, but the shape of the object has not changed. And this is called the rigid motion. Reflection. A reflection fixes a mirror line in the plane and exchanges the points from one side of the line with points on the other side of the mirror at the same distance from the mirror. Every reflection has a mirror line. Glide reflection. A glide reflection is a mirror reflection followed by a translation parallel to the mirror. Every glide reflection has a mirror line and translation distance. Even here, if you notice, The common point is just the position of the object has been changed but not the shape of the object. Hence, these four transformations have a common point of rigid motion. Reflections. Rotation of the object by 180 degrees is reflection. In reflection, the image is formed on the opposite side of the reflective medium with the same size. Hence, we use the identity matrix with positive and negative signs based on the reflective medium. Reflection about the x-axis. Here you can see in the picture, h, k is reflected about the x-axis and the reflected point is h, minus k. Hence, the identity matrix is 1, 0, 0, minus 1. And reflection about the y-axis, the point h, k is reflected about the y-axis and the resultant is minus h, k. Hence, the identity matrix of the reflection about the y-axis is minus 1, 0, 0, 1. Reflection about the origin, the point h, k is reflected about the origin and the resultant is minus h, minus k. Hence, the identity matrix is minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. Reflection with respect to the diagonal. The sequence of transformations required to obtain transformation matrix for reflection about the diagonal y equal to x are the following. Rotate the diagonal by 45 degrees clockwise, making it equivalent to the x-axis. Perform reflection with respect to x-axis and then rotate the diagonal by 45-degree anticlockwise direction to move the line to its original position. Now let us see how the reflections are done with respect to an arbitrary axis. Here let us assume the arbitrary axis as y equal to mx plus b, where m is the slope and b is the y-intercept. Firstly, translate the line by 0, minus b so that the line passes to the origin. Now rotate the line about the x-axis by minus theta. Then reflect the object about the x-axis. Now rotate back the line by theta and translate back by 0, b. Hence, we will achieve the reflection of the object about an arbitrary axis, where theta is tan inverse of m. Shearing is another type of transformation which produces a shape distortion. Here we are shearing in x direction and the resultant coordinates after shearing in x directions are x dash equal to x plus shx into y, y dash equal to y, where shx is the shearing factor and the matrix is represented as 1, 0, 0, shx 1, 0, 0, 0, 1. Shear in y direction. Y direction shear is given by the following matrix: 1 shy 0, 0, 1, 0, 0, 0, 1, where shy is the shearing factor in y direction, and after shearing the resultant coordinates are x dash equal to x, y dash equal to x into shy plus y. You can see in the picture the rectangle is sheared along the y direction with a shearing factor of 2. Raster methods. Rasterization is converting an image described in a vector graphics format into a raster image, that is pixels or dots, for output on a video display or printer or for storage in a bitmap file format. Raster methods basically focus on the pixels of the object in order to transform an object. For example, if we have to rotate an object by 90 degrees, we consider the pixel values to rotate the object. For example, we have a matrix with the pixel values 1 to 12, and if we have to rotate the object by 90 degrees in counterclockwise direction, we have to first reverse the pixel values in each row of the array and then interchange the rows and columns in the matrix. Hence, the resultant matrix is 3, 6, 9, 12, 2, 5, 8, 11, 1, 4, 7, 10. The same way, if we have to rotate the object by 180 degrees, the resultant matrix is 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Transformations between coordinate system. Computer graphics applications involve coordinate transformations from one reference frame to another during various stages of scene processing. To transform object description from xy coordinate to x-y' coordinate, translate so that the origin x0, y0 of the x-y' system is moved to the origin 0, 0 of the xy system, and then rotate the x-axis onto the x-axis. There is an alternative method, that is specify vector v that indicates the direction for the positive y-axis and then obtain the unit vector u along the x-axis by applying a 90-degree clockwise rotation to vector v. Rotation metrics could be expressed as elements of a set of orthonormal vectors. 3D transformations. When the transformations takes place on a 3D plane, it is called 3D transformations. Homogeneous coordinates of 3D transformation contains 4 components and the transformation matrices are 4x4 matrix. 3D point homogeneous coordinate is x, y, z and 1. 3D translation is same as 2D translation with an extra z coordinate and its homogeneous coordinates are 4. Hence, the 3D translation matrix is represented as 1, 0, 0, tx, 0, 1, 0, ty, 0, 0, 1, tz, 0, 0, 0, 1, where tx, ty and tz are the translation distances. 3D rotation is where an object can be rotated with respect to x-axis or y-axis or z-axis. Rotation with respect to z-axis. The resultant coordinates after rotating with respect to z-axis are x dash equal to x cos theta minus y sin theta, y dash equal to x sin theta minus y cos theta, z dash equal to z. Hence, the resultant matrix is represented as cos theta minus sin theta 0, 0, sin theta cos theta 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Rotation with respect to x-axis. The resultant coordinates after the rotation with respect to x-axis are represented as x dash equal to x, y dash equal to y cos theta minus z sin theta and z dash equal to y sin theta plus z cos theta. And the resultant matrix is represented as 1, 0, 0, 0, 0 cos theta minus sin theta 0, 0 sin theta cos theta 0, 0, 0, 0, 1. Rotation with respect to y-axis. The resultant coordinates after the rotation with respect to y-axis are represented as x dash equal to x cos theta plus z sin theta, y dash equal to y, z dash equal to z cos theta minus x sin theta. And the resultant matrix is represented as cos theta 0, sin theta 0, 0, 1, 0, 0, minus sin theta 0, cos theta 0, 0, 0, 0, 1. Three-dimensional composite transformations. To obtain a rotation matrix of an object which rotates with respect to an axis that does not coincide with the coordinate axis, we have to follow below 3 steps. Firstly, translate the object so that the rotation axis coincides with the parallel coordinate axis, and then perform the specified rotation about that axis, and then translate the object so that the rotation axis is moved back to its original position. Now let us consider another composite transformations in a three-dimensional plane, that is to rotate an object with respect to an axis that is not parallel to one of the coordinate axes. Then the series of transformations are: firstly, translate the object so that the rotation axis passes through the coordinate origin. Then rotate the object so that the axis of rotation coincides with one of the coordinate axes. Now perform the specified rotation about the selected coordinate axis and apply inverse rotations to bring the rotation axis back to its original orientation. Then apply the inverse translation to bring the rotation axis back to its original spatial position. Quaternion methods. A quaternion represents two things. It has an x, y and z component which represents the axis about which a rotation will occur, and a w component which represents the amount of rotation which will occur about this axis. The quaternion is defined as Q equal to W plus Xi plus Yj plus Zk, where W, X, Y and Z are all real numbers and I, J, K are all imaginary numbers whose value is square root of -1. The magnitude of a quaternion is given by the formula square root of W square plus Z square plus X square plus Y square, and the magnitude of a unit quaternion is 1. One of the most important operations with a quaternion is multiplication. Let us assume Q1 and Q2 are two quaternions which are defined as W1, X1, Y1, Z1 and W2, X2, Y2 and Z2. And the multiplication is done with respect to the components X, Y, Z and W. Quaternion multiplication is not commutative. Q1 into Q2 is not equal to Q2 into Q1. Quaternion methods are used in 3D rotations. They are very efficient method because they require less storage space when compared to 4x4 matrices, and they are important in animations which often require complicated motion sequences and motion interpolations between two given position sequences and motion interpolations between two given positions of an object. For the quaternion X, Y, Z, W, the corresponding rotation matrix M is defined as below. 3D scaling changes the size of the object and repositions the object relative to the coordinate origin. 3D scaling transformation matrix is represented as Sx000, 0Sy00, 00Sz00001. 3D reflection. Reflection in computer graphics is used to emulate reflective objects like mirrors and shiny surfaces. In 3D, reflection can happen with respect to x-axis, y-axis, z-axis, or also with respect to the planes zy plane, xy plane, and zx plane. Reflection related to a given axis are equivalent to 180-degree rotations. Now, with respect to x-axis, the identity matrix is represented as 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 1. That is x dash equal to x, y dash equal to minus y, z dash equal to minus z. Reflection about the y-axis in a 3D plane. As you can see in the figure, the object is rotated in 180 degrees about the y-axis. Hence, the resultant coordinates are represented as y dash equal to y, x dash equal to minus x, and z dash equal to minus z. And the identity matrix is represented as below. Reflection about the z-axis. When you see in the figure, the triangle is rotated about the z-axis in 180 degrees. And the resultant coordinates are x dash equal to minus x, y dash equal to minus y, z dash equal to z. And the identity matrix is represented as below. 3D sharing. Sharing changes the shape of the objects and they are useful for perspective projections. When an object is viewed from different directions and at different distances, the appearance of the object will be different. Such view is called perspective view. Perspective projections mimic what the human eye sees. For example, if we share the cube in the 3D plane along x and y axis, the perspective and the shape of the cube has been changed. Hence, the 3D sharing matrix is represented as 1 0 A 0, 0 1 B 0, 0 0 1 0, 0 0 0 1. Where A and B are the sharing factors with respect to x and y axis respectively. Here we end the discussion. If you have any questions, please do comment in the comment section and I'll get back to you soon. Thank you. Have a nice day.